Okay, here is the third video on graphing trig functions, and then we're going to do a couple of examples from 6.6 together. So let's go back to the sine graph, and you can apply the same with cosine as well, but here's the general shape of the sine graph. Very rough shape, I should say. Well, there's something that you maybe have heard in physics called amplitude. And the amplitude is thought of as the distance from the center line, kind of the still position, to the top of the crest or the bottom of the trough, crest or peak. So in the case of sine, this is just y equals sine x graph. We think of when there hasn't been any transformation of sine, so literally just dealing with y equals sine of x, the amplitude is 1, because the midline here is the x-axis. And now how high and below this resting position does the graph go? Well, it goes absolute value of 1 away. So it goes 1 away, or the absolute value. So the amplitude is always thought about as the symbol we use is little a, and you always report it as a positive number. So if I were graphing something like y equals 2 sine x, well, what does that mean? That means multiply all the y values by 2. So of course, any y value that's 0 stays the same, but 1, which occurs at pi over 2, would be up at 2 instead of 1. And so 1 gets multiplied by 2 rather. And at pi, I'm still at 0. And at 3 pi over 2, instead of being at -1, I'd be at -2. And so on. So this graph would be stretched vertically. With an amplitude, and it keeps going in the negative direction too. So the amplitude in this case would be 2. So that's something worth noting. Another thing is, well, what about, when does the period of a function change? Well, let me move this here. What about if we were graphing something like y equals sine of not x, but instead 2x. Well, remember that the crucial points we plotted before when we graphed just standard sine were 0, pi over 2 pi, 3 pi over 2, and 2 pi. If we wanted to just graph one period, and then we could extend that one period. Well, we're going to think about, what do I have to put in for x so that I'm actually taking the sine of 0? Well, in this case, you'd still put in 0. But what about for pi over 2? Well, instead of putting in pi over 2, in order to take the sine of pi over 2, I'd actually be putting in pi over 4. So if we remember back to our transformations of the past, whenever there was a transformation that occurred within the domain, then you are actually doing the opposite here. So this means, in this case, I'm doing a horizontal shrink by a factor of 2. So instead of plotting the 0 pi over 2 pi, 3 pi over 2 pi, I'm actually every point there, every x point that I used to plot is now being divided by 2. So I'm going to plot 0, then I'm going to plot pi over 4. Half of pi is pi over 2. Half of 3 pi over 2 is 3 pi over 4. And half of 2 pi is pi. So notice when I'm plugging in 0, I'm still doing sine of 0, so that would be 0. But when I plug in pi over 4, I'm doing sine of pi over 2, which I'm up at 1. When I plug in pi over 2, I'm doing sine of pi, which is 0. When I plug in 3 pi over 4, I'm doing sine of 3 pi over 2, which is -1. When I plug in pi, I'm doing sine of 2 pi, which is up at 0. And once you do one period, the idea is then you can extend it, keep on extending it in both directions. Like you'd have negative pi over 4, which are -1, and so on. An easy way to think about then how I could find a period of a trig function Well, this value in front of x we label as b. So remember before, just a little bit ago in this video, I said A stands for amplitude, the absolute value of A, in other words. Well, this b value tells me what the period is going to be. So in order to find the period of sine, and the same is actually going to be true for cosine as well, it's going to be, the period is going to be equal to 2 pi over b, which makes sense because it's if the original period is 2 pi, and if b is a value greater than 1, then we're going to be horizontally shrinking it. If b is a value less than 1, we're going to be stretching it, so multiplying by the reciprocal of that fraction b. So for example, if I had y equals cosine of 1/2 x, the period is going to be 2 pi over 1/2 x, over 1/2, don't need the x, sorry, just the coefficient. So it'd be 2 pi over 1/2, or 2 pi times 2, or 4 pi. So it's going to be stretched horizontally. So this is really no different than when we did transformations in the first semester. And then when I think about, okay, based on that new period, what points am I plotting? Well, you always divide the period by 4 to get your first bit of crucial points. If, again, this is as long as there hasn't been a horizontal shift. So if I'm plotting cosine of 1/2 x and the period's 4 pi, well, the interval width between my points is going to be 4 pi over 4, or pi. And in fact, that interval width wouldn't change if we did a horizontal shift too. Okay, let's pause and so we just talked about amplitude and period changes. Let's do an example in 6.6 to kind of get a feel of what's going on. Let's do number 1A in worksheet 6.6. And I'm asking you to do a lot here, so let's go through doing all this pieces. I'm actually not asking you to graph though in number 1. That comes later, but I'm asking you for a lot of information, which would be helpful if you go to do a graph. All right, start off easy here. The first thing I'm asking for is amplitude. Well, the amplitude, as I can see, is just 2, what's in front of that trig function. And that means it'll be, when I take my, my equilibrium or my resting line, that's how high above and below that line this graph will go. The period in this case is equal to 2 pi divided by, well, what's in front of that x or that angle? 3. So the period's going to be 2 pi over 3. How do I find a y-intercept? We'll plug in 0 for x. So my y-intercept, the x value is 0. The y value, if I plug in 0 for x, is 2 sine negative pi over 8 plus 1. And just leave it like that because we do not know what sine of negative pi over 8 is. The fourth bit of information, the general form for the x-coordinate of each peak. So remember, originally the peaks occurred for y equals sine x, the peaks occurred every pi over 2 plus 2k pi. So let's set the inside, because there has been a horizontal transformation, we're going to, because there's been a period change and a horizontal shift here, can tell that by looking at this here. Let's see where those peaks are changed. So to do that, and this is again the peaks part, I'm going to set what's inside my trig function equal to pi over 2 plus 2k pi. And we're going to solve for x because this will be the new representation of where the peaks occur. So to do that, I'm going to add pi over 8 to both sides. So I've got 3x equals Adding pi over 8, I get, let's see, 5 pi over 8 plus 2k pi, and then divide both sides by 3. So my peaks occur every 5 pi over 24 plus 2k pi over 3. And just to check here, since originally the peaks, if we were just graphing sine x, the peaks would occur every integer multiple of the period, which then was 2 pi. It makes sense that now they're occurring every multiple of the new period, which is 2 pi over 3. Okay, and let's then do our troughs, or our low point. So originally the troughs were every 3 pi over 2 plus 2k pi. So let's see where they are now. 3 pi over 2 plus 2k pi. All right, adding pi over 8 and dividing by 3. Let's just do this in one step here. We're going to get 13 pi over 24 plus 2k pi over 3. Finally, let's figure out our range. So our range, remember, normally our range is -1 to 1. So that would be what is coming out of the sine function. So you've got 2 times the range, what's coming out of the sine function, plus 1. And doing our range analysis like we would do before, we will get -1 to 3. So our range, that would be our range.